Hi everyone, welcome. Today we are going to discuss about part 5 of thermodynamics. In this part 5 of thermodynamics, we are going to discuss about these points first. So the first one, state and path functions. Second, work. Third, heat. Fourth, if we have still time, why work and heat are boundary properties. Okay, these 4 points we are going to discuss. So the first point here, what is state function and what is path function? Simple. If the function depends on initial and final states, is nothing but state function. If function depends on path, that is path function, right? So I will explain you in a very clear manner. See, so what is state function and what is path function? That is the first one. First, suppose time and distance both are path functions. Why time and distance are path functions, I will explain you. But just to explain you clearly about state and path functions and what is the difference between state and path functions, I will take one example. First, suppose you are there here, right? First, suppose you are there here. You are at your home. You are at your home, right? You have to reach to your coaching institute. Here your coaching institute is there, so you have to reach here home to coaching institute. For suppose to reach your coaching institute, you are taking 10 minutes time. You are taking 10 minutes time. If you go through this path, this is path number 1. Okay, now first suppose you are starting from your home. First of all, you are going to your gym. Okay, you are going to your gym. Then from this gym you are going to your friend house. From this friend house you are reaching to your coaching institute. Now from home to your gym you are taking 2 minutes time or 4 minutes time, right? From gym to your friend house you are taking 4 minutes time. Alright, from friend house to this coaching institute you are taking 2 minutes time. Okay, now 4 plus 4 8, 8 plus 2 10. So this is path 2. So this is path 2. Okay, so through path 1 you have taken 10 minutes time. Through path 2 also you have taken 10 minutes time. That means no matter what's the path is, but you are taking only 10 minutes time to reach your coaching institute. That means your state, you are just depending upon the state, not on path, right? Through path 1 you are taking 10 minutes time. Through path 2 also you are taking 10 minutes time only. So you are completely depends on state, not on path, because time is not changing here. For suppose here I am taking 5 minutes time, right? For suppose you are taking 5 minutes time here. Here 4 minutes time, here 2 minutes time. Total 11 minutes. So if you are going through this path, you are taking 11 minutes time. If you go through this path, you are taking 10 minutes time. Your time is changing, so it's a path function. If you go through this path, you are taking 10 minutes. If you are going through this path, you are taking 11 minutes. So you are a path function. This is the significant difference between the state and path function. Clear? Okay. So in thermodynamics, if you observe, only accept time, distance. First of all, why time is path function, why distance is path function. Generally, for suppose if I want to reach, again same thing, same example, if I want to reach from home to office, okay, through one path I am taking 10 minutes time. If I choose shortcut, then I can reach in 5 minutes. So completely time is a path function. Okay, so I can reach, if I take the shortcut route, then I can reach very fast, right? So time is a path function. Distance is also same. Distance, if I take long path, I have to cover 10 kilometer distance. Okay, if I take shortcut route, I have to cover 5 km distance only, right? So distance is also path function. So time and distance path function. In the same way, in thermodynamics, work, heat and heat capacity. Work, heat and heat capacity are path functions. Work, heat and heat capacity. Heat capacity. These three are path functions, except these three, and time and distance. Except these three, especially except these three, remaining everything in thermodynamics are state functions. Remember this point, very important point. That means if you take entropy, state function, pressure, state function, volume, state function, temperature, state function, internal energy, state function, enthalpy, state function, entropy, state function, Gibbs free energy, state function, Helmholtz free energy, state function, kinetic energy, potential energy, everything is state function except work, heat and heat capacity. So these three are path functions. These three are path functions. Remaining everything except work, heat and heat capacity are state functions in terms of thermodynamics. Okay, so remaining everything depends on state, only these three depends on path. Now, if I take the equation of first law of thermodynamics, delta U equal to Q plus W, right? We know Q is nothing but heat, so this is path function. Okay, so W is nothing but work, this is also path function, but this Q plus W which is equal to delta U. So why I'm writing delta U here? In thermodynamics, another important point, you can't write internal energy completely like this. So you cannot represent internal energy like this. Always you have to represent in terms of change. In terms of change. If you are talking about the internal energy, you have to write internal energy in terms of change. So delta U equal to Q plus W, this is the first law of thermodynamics. So in this, delta U is nothing but energy. Energy is a state function. So this energy which is equal to this. So this is nothing but your Q plus W. Individually Q is path function, W individually path function, but Q plus W is a state function because Q plus W is equal to delta U, right? Okay. After this, so this is about the state and path functions. Okay, so after this I'm talking about the work. So what is about the work? Simple. I'm taking, for suppose, right, I'm taking here beaker, right? Here gas molecules are there. Okay, now here I'm closing this one, right? This is the closed container. Here piston is there and I'm applying pressure here, external pressure, right? External pressure is there. Now I have external pressure from the surrounding. Gas has some pressure, that is nothing but your internal pressure, pressure of the gas. Pressure of the gas is also there. Now system has some energy. For suppose system has E1 energy. Now this surrounding has E2 energy. Okay, now energy will transfer from the system to the surrounding as well as surrounding to the system, that is nothing but work. See, I am here, right? You are there. I am applying some force on you. This is the process. So whenever I am applying some force on you, that means my energy is transferring towards you. For suppose you consider me as a system, except me everything is surrounding. You are also surrounding to me. So my energy is transferring towards you. For suppose if you are pushing me like this, okay, for suppose if you are the system, I am the surrounding to you. So from you to me, energy is transferring. So whenever energy is transferring from the system to surrounding, or energy is transferring from the surrounding to system, that energy transfer is nothing but your work. So whenever during this process work is happening, right? So energy will appear in the form of work whenever transferring of energy occurring. Okay, so this is about the work. Okay, so whenever I'm applying the external pressure from the outer side, from the surrounding side, now some gaseous pressure is also there, like this, in this direction upward. This is in the downward, this is in the upward. Okay, so work is happening. Okay, now what happens? I have one formula for work. I have one formula for work. What is that formula? Work done equal to force into displacement. So work done equal to force into displacement. Okay, so what is displacement? I'm taking again, for suppose I'm taking this beaker, right? I'm taking this beaker. So here gas particles are there. Okay, so initially my gas level is this. Initially my gas level here. Okay, so after applying some external pressure, because of compression of the gas, my gas level now here. Okay, my gas level is now here. So here first of all the gas is there. Now here, so there is a displacement. The gas displacement is like this. Okay, and I'm applying some force here. I'm applying some force and there is a displacement. First of all my gas level is this. After applying some pressure, compression takes place. So during compression the gas level now here. Okay, so there is a displacement. So I can write work equal to force into displacement. Work equal to force into displacement. Okay, so work equal to force into displacement. Okay, now I know pressure equal to, okay, pressure equal to force by area. Why? Pressure is nothing but thrust. Okay, so how much force you are applying on unit area of the surface, that is nothing but thrust. Thrust is nothing but pressure. So pressure equal to force by area. Pressure equal to force by area, right? So force equal to pressure into area, right? Force equal to pressure into area. So I can write in place of force I can write pressure into area, right? Displacement I can write as ds, right? Now area into displacement is nothing but change in volume. So I'm writing here pressure into change in volume, dV, W equal to PdV, right? Okay, I'm applying external pressure here. So when I'm applying external pressure here, what happens? Gas molecules are just going down, right? Internal pressure is also there. Pressure of the gas is also there. It is moving upside. That means the motion of the gas particles are against to the internal pressure. That means external pressure is just opposite to the internal pressure. That means minus, opposite to the minus, opposing force. If I am applying external force like this, the gas molecules are moving. So the motion of the gas particles are against opposing force. Opposing force is there from the downside, right? So the gas particles are moving against opposing force. So minus. So W equal to minus PdV I can write. So W equal to minus PdV. This is the work formula. W equal to minus PdV. This is the formula of work. Okay. Then what is work done by the system and what is work done on the system? This is very important. See, first of all, work done by the system. Work done by the system. So what is work done by the system? Simple. System's pressure of the gas, if higher than external pressure, then what happens? Expansion takes place. Okay, I already discussed about this expansion compression in my last class. So whenever pressure of the gas is higher than external pressure, when pressure of the gas is higher than external pressure, then it leads to expansion. Right? It leads to expansion, right? When pressure of the gas is higher, the gas molecules are moving upward. The gas molecules are moving upward. So whenever it happens, expansion takes place because pressure of the gas is higher. So whenever expansion takes place, simply see. For suppose the gas level is this now. Okay, the gas level is this now. External pressure and pressure of the gas. Okay, here the gas level. So whenever the gas particles are moving, because pressure of the gas is higher, gas particles are moving upside. So my gas now is at this level. Okay, is at this level. Now this is my initial volume. Okay, this is final volume. Okay, this is the initial volume, this is the final volume. That means whenever expansion takes place, listen, whenever expansion takes place, initial volume is this, after expansion final volume is this. That means final volume is higher than initial volume. Final volume is higher than initial volume. So how can I write? W equal to minus PdV, change in volume, that means volume of final minus volume of initial, right? Volume of final minus volume of initial, that means minus P into volume of final is higher than volume of initial. That means this value is positive. For suppose this is 5, this is 2, 5 minus 2, 3. So this is positive. So whenever it is positive, minus plus negative, so W equal to negative, right? That means W equal to negative work done by the system. Work done by the system is negative always. If in question examiner will give work done by the system term, then you have to choose the option which is having negative sign. Okay, so work done by the system is always negative. Okay, now work done on the system. Work done on the system. See, work done on the system. Here external pressure or pressure of the gas is less than external pressure. Pressure of the gas is less than external pressure. So when pressure of the gas is less than external pressure, what happens? Compression takes place. Instead of expansion, compression takes place, right? So here compression takes place, right? Why? For suppose, so initially now my gas is at this level. Okay, initially my gas is at this level. Okay, now I'm applying external pressure. Now external pressure is greater than this internal pressure of the gas. Now what happens? Because of compression, my gas level is reaching to this level now, right? My gas is reaching to this level now, just opposite, right? Now initial volume Vi is this. Now final volume Vf is this. That means my initial volume is higher. Initial volume is higher. So when initial volume is higher than final volume, I can write, for suppose, minus P, here Vf for suppose 3, here initial volume is higher, 5, that means negative sign, minus 2, minus minus plus, that means W equal to positive. So during work done on the system, W equal to positive. W equal to positive. This is also very, very important. So work done by the system, W equal to negative. Work done on the system, W equal to positive. Clear? Okay. Next, work done against free vacuum. So what is free vacuum? Free vacuum means closed. This is not a closed container. Work done against free vacuum. Work done against vacuum. Okay, and work during free expansion. So whenever we have free vacuum, expansion is free. Okay, because it is not a closed container. So whenever it is not a closed container, piston is there. Okay, so only inside pressure is there, external pressure is not there. External pressure tends to 0, right? See, to happen any work, external pressure should be there, internal pressure also has to be there. For suppose I am here, I am applying some force on you, we are doing fighting, I am applying some force on you, right? You have to apply some force on me, right? If you don't apply any force, there is no question of fighting, right? In the same way, if external pressure is absent, because it is vacuum, it is open, so external pressure is not there. So external pressure in these two cases, external pressure is tends to 0. Okay, whenever external pressure tends to 0, what happens? From the inside, pressure of the gas is there, right? Whenever pressure of the gas is there, piston is moving very fastly to the upside, right? With a very high speed, piston is moving towards up. But to stop that movement of piston, from the outer side there is no pressure. There is no pressure from the outer side to stop the movement of piston. From the inside, pressure is there, piston is moving with a very high speed, but from the outer side there is no pressure to stop the movement of piston. So whenever external pressure is not there, work will not happen, so work is 0. So in both of these cases, when external pressure is 0, so W equal to 0. Very important point, right? Work done against vacuum and work done during expansion, W equal to 0, because external pressure tends to 0. Clear? So this is about the work. So why work and heat are boundary properties? That is very important. Dekho, next, heat. So what is heat? I am taking one container here, right? I am taking one container. Again, gas particles are there here. System energy at E1, surrounding energy at E2. Okay. Now, for suppose system is at T1 temperature, surrounding is at T2 temperature. System is at T1 temperature, surrounding is at T2 temperature. Now, energy is moving from the system to the surrounding. In any process, energy is moving from system to the surrounding and surrounding to the system. This is clear? Okay. So, whenever energy is moving from the system to the surroundings and surrounding to the system, the condition is energy has to move from high temperature to the low temperature, right? If energy will move from high temperature to the low temperature, energy will convert to the form of heat. In that case, energy will be called as heat. Clear? So I will explain you about this heat, okay, and why heat and work are boundary properties. I will explain you in the next class. Okay, so in this class, up to this only. Okay, so first of all, I explained you about the state function and path functions, which is state and which is path. And next, what is work? What is work done by the system? In work done by the system, W equal to negative. Work done on the system, W equal to positive, is very important. And work against a vacuum, W equal to 0, because external pressure tends to 0. And during free expansion also, work done is 0. So this is about this. Today's class, I will explain you about the heat, why work and heat are boundary properties. That is very important. Always work appears at the boundary of the system. This is very important. I will explain you very clearly. Okay. And next, what is internal energy? You have to study. Okay. What is the internal energy? These all things we will study in the later classes. Okay. So that's all for this video. Thank you so much for watching. Have a nice day.